Okay, now we will study serial transmission using UART. UART is Universal Asynchronous Receiver Transceiver. There are two jobs of UART. It can be either used as a transceiver or it can be used as a receiver. So you have a sending UART and now you have a receiving UART. Okay, so if it's a transmitter, it will take the parallel data, and then transmit it serially. But on the receiver side, it will receive
data
serial data, and then it will transmit it parallel to the receiver. So now you have a transmitter and now you have a receiver. Why UART is used? Typically UART is used when there is a single line between the transmitter and the receiver. Okay, so the protocol for this UART is RS232. RS232. You can give, have the details of this RS232 data sheet. You can have its details in the data sheet. Okay, but now I will explain the concept of UART. So in UART you only need one serial line. So you need reduced number of pins. The number of pins are reduced. But then you need a protocol. Then you need a protocol between the transmitter and the receiver. That was the protocol of transmission. So the protocol of transmission is like this. So if we have a serial data, so when the bit is 1, it means there is no data. When it starts from 0, it means now it's the start of the data. So it's the start of the data. It's called as start bit. After that, now you have some data bits. D0, D1, D2, so far so on. Let's assume D7. So what is the size of the data bits? 8 bits. So now we are transmitting 8 bits of data, and in the last you have a parity bit. It can be an even parity or odd parity. So the parity bits can be used to detect the errors. Okay, there can be a single parity bit or there can be multiple parity bits. In this case, we assume that now we are using only a single parity bit. And now there is a stop bit. So start bit indicates the start of the transmission, and the stop bit indicates the end of the transmission. And this transmission is asynchronous. Okay, now the important thing between the transmitter and the receiver is the baud rate. Baud rate will tell us the duration of the bit. That what should be the duration of the bit. So now let's assume if we have a baud rate of, so different baud rates are like 1920, 3840 and so forth. There are different baud rates. So there are different baud rates. Okay. Now if the baud rate is 1920, it means that we are able to transmit 1920 bits per second, and it determines the duration of the bit. So if you look at here, so now this is a bit duration. This is a bit duration. This is your bit duration. So if we increase the baud rate, what will the impact on the bit duration? The bit duration will reduce or increase? The bit duration will be shrink. So now let's say if we increase the baud rate, so it will look like this. So now you have start bit, stop, and then D0, D1 up to D7, and then parity bit, and then stop bit. So this bit duration is determined by the baud rate. Okay, now when you are sending the data, and now you have a receiver, so both the transmitter and the receiver should be configured at the same baud rate. If the baud rate is different, so actually you will not receive correct data. So they should both be configured at the same rate. Okay, now if you are using a receiver, and we are at the receiver side, we are at the receiver side, and we want to design a controller for the receiver side. So how the controller can be designed? Now if we look at here, to sample the data, where should we sample the data? Should we sample the data in the middle, or should we sample the data here in the middle or on the edge? Where should we sample the data?
Edge.
Why H? Because there is a transition from 0 to 1. So will we get stable data, unstable data? So if we say that now we are making a start and if we sample the data here, will we sample correct data or incorrect data?
Incorrect.
Incorrect data. We may sample incorrect data. So actually to sample a correct data, we should sample the data in the centers. Because in the center the data is stable. Okay, now if you want to design a controller for this, so we need a clock. We need a clock. This clock, now you need the Nyquist criteria. The sampling frequency should be at least
Twice of
the input frequency. Now let's do it if we have a clock. Now you have clock. Now this is our clock. And within this bit duration, we have a sample clock. We have a sample clock. And within this bit duration, there are 8 clock cycles. There are 8 clock cycles. Now, if the sampling frequency, now in this case, the sampling frequency is 8 times the sampling frequency is 8 times the input frequency. Input frequency. Okay. Now, if we want to sample the data, so now we can have some kind of a state machine. So in the restate, so in this case, the state is now idle. Idle means we are not receiving any data. Okay. Now, how does the receiver know that now is the start of transmission? So it should look at the bit. SB stands for serial bit. Now there are two possibilities. Either the bit is 1 or 0. If the bit is 1, what does it imply? No data. So it will again 1. If it is 0, then so now we need start. It means now we are getting some start of the data. Like let's assume it's here, so it means that now we are getting start. If it's 0, now it's 0. So then we need to reach the middle of this bit. So we need a counter. Counter is equal to count plus 1. And in this idle case, we should initialize the counter to 0. Counter is reset to 0. Now in this case, count is equal to count plus 1. Okay, now this counter, okay, where should we check for the counter value now? Until we reach the middle. So when will you reach the middle?
8.
When the count is 4.
4, yes sir.
Because during this cycle,
8 clocks.
8 clock cycles. So now we have reached the middle. So then you will see for the count value, if count is equal to 3. If count is equal to 3, then you say you will remove this start bit. Okay, now if we want to reach the middle of T0, how many clock cycles we need?
8.
8. We need 8 clock cycles, so you need 8 clock cycles. And to reach, okay, now in this case, when count reaches
7.
4,
4.
so then we should reset the counter.
Yes sir.
And until this, count is equal to 1. And now bit count will be what?
1.
1. Now we have sampled the
First bit.
first bit. Now when you reach the middle of D1,
After
again we will reset the counter. When the count will reach 8, okay. Count is 4, we will reset the counter. When count again, when it reaches its maximum value, then we will reset the counter and the bit counter will be incremented.
by 1.
Bit counter will be bit counter plus 1. Again, counter will again be initialized to 0. In this case, what will be the value of count? When counter reaches 8, what will be the bit counter now?
2.
When we will sample the last bit?
8.
When bit count will be 8. So actually now we have reached the middle of the last bit. Okay? And when we will reach the middle of the parity bit?
After 8 clocks.
After 8 clocks. So initially we can use a shift register. We can use a shift register. At this point, we will move D0 here. At this, when bit count is 1. In the next class cycle, what we will do? We will shift the data And in the next clock cycle, what will be the value? And in the last clock cycle, what will be the value?
D7,
D7,
D0.
Up to D0. So in this case, now we have sampled the last bit. And now this data is now in the register. So now it has received the serial data. It has received the serial data and transferred it parallel. Now the data is bit. Okay, now we also need to check the parity bit. When the data is in the register, we call it as a latch or data register. Data register. And now we will assemble the last parity bit. So now let's assume if it is even parity. And the data we have received is 1 1 0 0 1 1 0 0 and the parity bit is 0. Is there an error in the data or no error for even parity?
No error.
There is no error because the number of ones are
Even.
But if parity bit is 1,
There will be error.
there is an error. So actually now if you look at the design of the receiver, so at the design of the receiver, so the receiver is actually receiving the data serially. It has a sample clock that runs faster than the input frequency, whose frequency is higher than the input frequency. Now let's assume if in this 1 bit duration, the number of sample clock cycles are 24. So to reach the middle, how many clock cycles we require?
12,
12. And to reach the middle of the next bit,
24.
we need 24 clock cycles. We need 24 clock cycles. So all these parameters are set by the baud rate. Now if we have one sampling frequency and if we change the baud rate, so the number of clock cycles will also vary. If the clock frequency is same. Now let's assume if we have here within the 1 bit duration there are 100 cycles, and if we increase the baud rate by 1, so then within 1 bit duration how many clock cycles will be there? Assuming that the sampling frequency is same, if we double the baud rate, so in 1 bit duration how many clock cycles will be there? 50.
नहीं सर.
Double the baud rate.
ठीक है वो Nyquist ठीक है.
Now let's assume if we have in the 1 bit duration, there are 100 clock cycles. 100 clock cycles of the sample clock. If you double the baud rate, the bit duration is now reduced to half. So within the same 1 bit duration,
It will be 50.
it will be 50 clock cycles. And if you further increase the baud rate by 2,
25.
then 25, and so forth, so on. Okay, so in the designer of the receiver, you have multiple parameters. One is the baud rate,
Yes.
one is the sampling frequency, and it also depends upon how many bits you want to transfer. In this case, how many bits are you transferring? 8 bit of data. Whether the parity is even parity or
Odd pair.
odd bit. Now, if you want to transmit the data, so actually, what is the overhead? The overheads are 3 bits. One is for the start bit, that indicates the start of the transmission. One is the stop bit, that indicates the end of the transmission. So in this case, if you look at the overhead, so the overhead is actually 3 divided by 3 plus 8 multiplied by 100. Why 3 bits are used? One for the start bit,
One per stop and one
for stop bit, and one for the parity. Now in this case we have assumed that we are using a parity bit. So parity bit can be even parity or
odd pair.
odd parity, and parity bit can be used to detect the error. It cannot correct error. But if you want to correct the error, so we can use the Hamming code. In the Hamming code we may need multiple bits,
Yes, sir.
and when we need multiple bits,
The overhead increases.
so the overhead is increased. So these are the parameters. That needs to be considered for the transmission of the data using UART. So the parity bit is the extra bit for error checking. So we have start bit and stop bit, and now the baud rate. The baud rate determines how the signal changes per second. whether it's changing fastly or, and bit rate is usually higher. The bit rate is usually higher. So it's all the parameters of a UART. Okay, now stepper motor. G. What's a stepper motor? What's the difference between the DC motor? We have studied a DC motor,
Yes, sir.
and we were controlling that DC motor using PWM signal.
Yes, sir.
Okay, now if you differentiate between the DC motor revolves continuously, and stepper motor revolves in steps.
Yes, sir.
In steps. So now if we consider one circle, so now it's the circle. So these are steps. Okay, if you look at this circle, so it's actually 360 degrees. If the total number of steps are 60 steps, total number of steps are
4.
60. So what is the step size?
60, 360 divided by 60.
6 degree.
Yes,
So
sir.
it will be moved in one step by 6 degrees. So it will move by 6 degrees. If the number of steps are 30, so what is the step size now? 12 degree. So it rotates fixed number of degrees when given a step signal. Fixed number of degrees. The degree can be either 6 degree or 12 degree. It depends on the number of steps in one revolution. Okay. In contrast, DC motor just rotates when the power applied.
Yes, sir.
In a DC motor, we have an RPM. What is RPM? Revolution per meter. And the RPM was decided by the PWM signal. So in the previous example, if you so here if you look at here, so if the PWM signal is 0, the RPM was 0. If it is 2.5, RPM was 1840 or 3.756900. So when we are increasing the input voltage or the PWM signal, so the RPM increases.
सर इस इसमें ये साइकिल हाई क्या है?
क्या?
सर चार्ट में ये साइकिल हाई क्या है?
Where? कहाँ पे?
सर ये एक ब्लॉक डायग्राम के ऊपर
8-bit
कंपैरेटर के नीचे से साइकिल हाई.
Madam, this is the method in which you are generating a PWM signal. How do you generate a PWM signal? आपको मैंने कहा था ना कि let's assume if we have 256 counter, 256 bit counter, and if you want to generate a PWM signal of 50%, so if it is from 0 to 127, it will be high. From 128 to 255,
Low.
it will be low. So now you are generating a PWM signal of 50% duty cycle. Now if you want to generate a PWM signal of 25%, from 0 to 63 it will be high. From 64 to 255 it will be low. So this is a simple algorithm. How you will generate a PWM signal using microcontroller. So if you look at the stepper motor, now if you look at the sequence, what is the sequence? Now if you see here, so there are different coils. What is the name of coils? A bar, and then
B bar.
B bar. So these are the coils, and then we apply some voltage. Plus 10 for positive voltage, minus 10 for ground. Plus 10 for positive voltage and minus 10 for, and now it's the sequence. Now if you want to produce a step, so now you have, so if you look at here, so this is plus, plus, minus, minus. Now if you want to go to this step, so now you have to rotate it. So minus will move here, minus, plus, plus, minus, and then it will rotate here, minus, minus, plus, plus, then plus, minus, minus, plus. So it's moving. So now if you repeat this sequence, it will move by one step. So now this is the, if you look at this IC MC3479P, so there are, if you look at here, CW bar and CCW. What does CW bar?
Clockwise or counterclockwise.
CCW. So when it's 0, it will move in a clockwise direction. When it's 1, it will move into counterclockwise. Why? Because there is a bar. Bar is active low. So when it's 0, it will move in a clockwise direction. If it's CCW, it's 1, it's anti-clockwise. Now it's the full bar and half step. Full bar. Full bar and half step. When it's 0, so it is full step. When it's 1, it is
Half.
half step. So maybe the full step is 12 degrees and the half step is
6 degrees.
60. Depending on the specification. First you have to look at the specification. That what's the step size? So it depends on the specification and you have to look at the specification. And now there are some clock because you have to give the accelerator clock and OC. You can look at the data sheets. So the rotation is achieved by applying specific voltage sequence to the coil. Specific voltage sequence to the coil. And now you are applying different coils. Now there are coils A minus bar, B minus bar. And now when you shift this bias voltage, so actually the rotation can be achieved. Okay, now if you look at here, this is stepper motor without controller. Now, if you look at this code, white and white, and look up, there are 20 values. Why there are 20 values?
20 steps.
Because if you look at the sequence of that step, so it is plus, plus, minus, minus, the same sequence. If you remember, there are 5 sequences. Plus, plus, minus, minus, then minus, plus, plus, minus. So actually, if we code this in binary, so this is 1, 1, 0, 0. The second sequence is 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, and 1, 1, 0, 0. So these are different sequences. Okay? Now if you look at this code, and look up. So this is sequence number 1. This is sequence number 2, 3, 4, 5. Now while loop. You are having a while loop. It will run indefinitely. Move 1, 2. It will call the function move. DIR sets the direction. Okay? And steps is the number of steps. Okay, now direction is equal to 1. It will be clockwise direction or anti-clockwise direction. Clockwise direction or anti-clockwise direction. Now, for y is equal to 0, y is smaller than number of steps. What are the number of steps? Here, have they defined steps?
15 degrees है सर, तो steps 360 divided by 15.
Steps. So now we have 2 steps or 1 step. So in this case, move forward 15 degrees. 15 degrees. And now move backward 7.5. Why this 1? 1 sets the direction. Clockwise, and this is anti-clockwise. And now if you look at here, if you look at the bits, S bit direction P2.4. So it means that the motor is connected with P2.4. What is the bit 2.4? 2.4 is connected with which pin? P2.4 is connected with which pin? डायरेक्शन बिट. डायरेक्शन कौन सी बिट होगी वहां पे? चलो अब यहाँ पे दोबारा मैं कर देता हूँ. It will be connected with pin number 10. Pin number 10 of what? Stepper motor. ठीक है? So pin 2.4 of the microcontroller is connected with pin number 10 of MC3479. So when this direction is 0, it will move in clockwise, otherwise it's 1 anti-clockwise. Okay, now if you look at here, just look at this code. Is B, not A, not B? Is A, is B, not A, not B? If you look at the code, okay?
Sir, ये without controller.
Without controller, yes. Okay, now what's the pattern? 1, 1, 0, 0, then 0, 1, 1, 0, then 0, 0, 1, 1, then
1001.
1, 0, 0, 1, and then
Double
1, 1, Okay, now this is, if you remember, it is sequence number 0. Sequence, okay, 1, sequence 2, sequence 3, sequence 4, or sequence 5. Okay, now there are two bits. One is A bar, B bar. So is A is actually A. Is A is actually A. Is B is actually B. So this is A. If you look at the sequence before, A, B, A bar, B bar. A, B, then A bar and then B bar. Okay, now if you look at here, if you look at this code for Z is the loop variable. Z is the loop variable. Okay, now Z is equal to 0, Z is smaller or equal to 19. Why is smaller or equal to 19? If you look at this array, look up 0. This index is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And the array index starts from 0. So this is look up
1,
0. And look up
19.
19. Okay, so now this is look up 0. This index is, if you look at here, this index is 0. 1, 2, and 3. Okay, now is A. Okay, Y is equal to Z is equal to 19. Is A is equal to look up Z. Achha, what will be the value of is A? Initially, what will be the value of Z? 0. At this point, what is Z? 0. So is A is equal to look up Z. Is A will be 1. Is A is equal to look up Z, and what is the value of Z? 0, 1. Then is B is equal to look up Z plus 1. What is the current value of Z now? 0. Z plus 1 is 1. 1. What is not A? Look up 2. 0. And not B. Look up 3. What's its value? 1, 1, 0, 0. So this value is 1. Is A is 1. Is B is 1. Now you apply this pattern. Now we increment Z by what? 4. Because we want to jump here. So now what's the value of Z here?
4.
4. The value of Z is now 4. When the value of Z is now 4, it is moving, it is now pointing to the base
Of the next sequence.
the base of sequence 1. In the next iteration, what will be the value of Z?
8.
8. In the next iteration, 16. In the next iteration,
12. 8 के बाद 12.
8 by 12. And then
16 to 0 है.
okay. Now when you apply this sequence, so you apply this 1, 1, 0, 0, which is positive, positive, negative, and negative, and then you have a delay, because when you move to by one step, you give a delay, and then delay can be configured. So if you look at the delay routine, so what you are doing? You are doing nothing. You are just
Counting.
no. You are just causing a delay.
Counting.
Because for A is equal to 0 is smaller than 5000, B is equal to B is smaller, and A is equal to A plus 0. You are just like doing nothing here.
Executing some unuseful instruction.
And it's unuseful instruction, just like a knob. So if you want to implement this delay in assembly, so we can initialize some register with very large values.
Yes, sir.
We can then decrement it register,
Yes, sir.
and then we compare this instruction with
0.
and when it is not equal, it will jump again back to the loop. And when it reaches 0, it should exit out of the loop, and then we have a return. So you can see, what is the delay routine? Delay can be like this. Move R0 with some large value, decrement
Increment R0.
R0, compare
R0 with
R0 with 0, branch not equal,
delay.
delay, and RET. And if you want to call this delay, so we can say call
Delay.
delay. So actually this is the assembly equivalent of the delay subroutine, and now this is the C equivalent of the delay. So now we are sending some pattern. So what pattern will be sent? 1, 1, 0, 0. In the next iteration, what will be the value of Z? 4. So the next value of Z will be 4. What will be the value of is A? 0. What is the value of is B? 1. Is C? 1. And is D?
0.
0. Now we will satisfy. So this is the index is now 5, 4, 5, 6 and 7. Then 8, 9, 10 and 11. So now this is the code that how you will interface a stepper motor without control. And now it will be controlled by the microcontroller. Okay, now if you look at here, if it's very important. Now there are 4 pins, P2.0, 2.1, 2.2 and 2.3. So is A actually connected with P2.1? Here. Not B is connected with P2.2. Is B is connected with P2.3 and all these pins. So if we look at the stepper motor and FC this. So what is pin number 2? What is pin number 2 of MCB?
A dash.
A bar. So it is not A. Pin number 3 of
A.
MCB is A. Is A. Is A. Achha, now there are two pins. One pin is from the microcontroller. One pin is from the motor. So actually, is A is connected with pin 3. Not is connected with pin 2. Okay.
Is B connected with?
Is B is connected with pin 13. Not B is connected with pin 14. Okay. And then CW bar and CCW.